We have energy sources that don't get used up and will not run out. These include things like biomass and biofuel, hydroelectric power, wind power, and solar power. Biomass is used to generate electricity in much as the same way as fossil fuels. It's just burning other things instead of coal or natural gas. It's not burning those fossil fuels. It's burning things like wood, garbage, and some other plant materials are used, like leftover husks from almonds and things like that get burned in biomass. And biomass can also be used to turn it into biofuels like ethanol or biodiesel. So we can kind of use some much quicker plant material and some chemical processes to turn those into things similar to things in the processes that we generate energy from our fossil fuels. Biomass are used in industrial applications, transportation, and electricity. We only use biomass for about 1.5% of our total electricity, but it is a growing market. And biodiesel and ethanol, some of those biofuels, can be used to replace or reduce the amounts of petroleum or oil that we use in our cars and trucks. Biodiesel is a way to replace other types of gasoline and fuels in our vehicles. One of the advantages is it's renewable. We can regrow these plants much quicker than we can use them, or on a similar pace to we use them. And it can be used in some of our current infrastructure. Burning biomass like wood or garbage can occur in some of those same power plants that used coal or natural gas combustion. But anytime you're burning something, you're going to be giving off some CO2, and that's negative. That's a greenhouse gas that's got some concerns. But most biomass and biofuels also need to be grown in the places where we grow our food. Corn and soybeans are two things that are very commonly used in biomass and biofuels, and corn and soybean that's grown for biomass and biofuels is corn and soybeans that are not available as food. Hydroelectric power is another very common renewable energy source, and it uses gravity and flowing water to turn a turbine. Instead of boiling water and using steam to push the wheels on a turbine, it uses gravity. These can occur in things like a dam where they build a giant lake to create a gravity-fed turbine. It can be used in a water wheel on a river. Or there's a lot of development going into tidal power, where the gravity pulls on the oceans to create our tides, and the movement of the tides in the ocean can turn those turbines. Water's been used as power for over 2,000 years. The Greeks started using water wheels and the power of water to turn stones that ground wheat into flour to help them make their breads. Solar energy from the sun also starts out in this process. A lot of the energy to move water around comes from the sun, and that helps to evaporate the water and create our water cycle. Hydroelectric power helps to provide about 7% of our electricity, and it is the cheapest way to generate electricity. Its cost per unit of energy is the lowest. Hydroelectric power is renewable, cheap, and efficient. It is the least expensive to produce, and it's very, very, very efficient. Very little of the energy from that gravitational potential of the water is lost in forms that are not used to convert to electricity. So you get very big bang for your buck. You don't lose a lot of that energy in forms that aren't creating electricity. It's very efficient. Hydroelectric power can only be used in certain areas. You can't build a hydroelectric power plant in the desert. You have to have those water sources. And as climate change is occurring, some of those areas that used to be useful for hydroelectric power may not be so useful here in the future. And then whenever you build a dam to create that reservoir of water and power your hydroelectric dams, you're changing the ecosystem. It really displaces and completely changes the river that it's in. That can change the water temperature and can completely change the type of species that can survive there. Wind power is another very common renewable energy source. Energy from the sun, once again, it's all starting with energy from the sun. heats up the air differently in different places. As hot air expands, it spreads out and cool air rushes in. This creates wind, that cycling of different air molecules throughout the atmosphere. And that's all due to different heating, the sun heating different areas of the earth different amounts. As that wind turns, as that wind blows, it turns the blades on a windmill, and those blades on the windmill turn a generator. Once again, wind power originates from the sun. It's also a source that's been around for a very, very long time. Ancient Egyptians and Persians, what's now present day Egypt and Iran, have been using wind power for over 5,000 years. It's used to create about 6% of our electricity, and it's one of the most fast growing energy sources. It's really, really, really making advancements and being used much, much more here recently. And you need about a consistent 8 to 16 mile per hour wind to be able to generate electricity. And that's why you see them get so tall. The higher up you go, the more consistent winds you get. So by having very tall windmills, they can reach some of those speeds much easier. Again, it's renewable, which is an advantage. Wind power doesn't create any air or water pollution. You can put lots of windmills in an area. You can put lots of windmills in the same spot. As long as the blades won't hit each other, you can keep them pretty close to each other. And then there's quite a large area of the US that has wind speeds that can be useful for wind power. It is not very efficient, though. Only about 25 to 45% of the energy from the original wind actually gets converted into electrical energy. So only about half of that power that's in the wind is able to be harnessed. And that's one of the drawbacks right now, but they're getting better at that. It can be harmful to birds and bats that can fly into the blades and die. And then if there's no wind, well, you don't get any electricity. It can only occur when the wind's blowing. Solar power is our final renewable energy source, and this one's quite different because it's the only one that doesn't, in some way, shape, or form, turn a turbine generator. It does generate electricity in a couple of different ways, one of which is actually heating something up and turning a turbine, kind of like using a magnifying glass. Solar concentrators reflect the sunlight from mirrors onto water, and that water or those fluids are heated up and create steam and turn a turbine that way. But solar concentrators are not very common. They're used in much more specific locations. The other form is photovoltaic cells or solar cells, and those are the only ones that don't use a generator. And they occur by a chemical reaction where sunlight actually knocks electrons off of atoms, creating ions, and those ions are used to form an electrical charge, stored electrical charge in the form of almost like a battery. And those electrons can then flow as they try to move back to that balanced charge. Solar cells can be a little confusing. They're so different from the other ways that we generate electricity. It's helpful to take a look at a short video.
You probably know that plants get their energy from the sun through their leaves in a process called photosynthesis. We humans don't have our own leaves, but maybe we can get energy from the sun in a different way. Electrical energy, that is. Could there be some kind of electrical leaf? A solar cell gathers light from the sun and generates electricity, just as a leaf generates food for a plant. Let's find out how. The sun emits energy in the form of waves. These waves can range in length from short ultraviolet waves through the rainbow of the visible spectrum to long infrared waves. When the sun is shining, these waves move towards the Earth and hit the surface of the solar cells. Let's take a closer look. The active part of a solar cell is a wafer made of semiconductive material, typically silicon. A semiconductor is a type of material that normally normally doesn't conduct electricity well, but it can be made more conductive under certain conditions. The semiconductor part of the solar cell has three layers. The thin top layer contains silicon and a very tiny amount of an element such as phosphorus that has more electrons than silicon. This gives the top layer an excess of electrons that are free to move and make the material more conductive. The top layer is also called negative type or N-type, as it favors the collection and transport of electrons. The thin bottom layer contains both silicon and an element such as boron that has fewer electrons than silicon. This gives the bottom layer fewer electrons that are free to move, therefore making the material less conductive for electrons. A missing electron can be described as an effective positive charge. Therefore, the bottom layer is called positive type or P-type, as it preferentially favors the collection and transport of these positive charges, also dubbed holes. The thicker middle layer has only slightly fewer electrons, making it marginally P-type. Thin metal lines, typically made of silver, are printed on the top N-type layer, and the bottom P-type layer is in contact with an aluminum plate. When light waves hit the top surface of the silicon solar cell, only light with wavelengths from a specific window of the solar spectrum, 350 to 1140 nanometers, are absorbed into the middle layer of the solar cell. This range of wavelengths includes the visible spectrum. Ultraviolet wavelengths are so short they stop at the surface, and infrared wavelengths are so long they can't be absorbed and pass right through the cell or are reflected back. The light wave knocks an electron off a silicon atom, setting the electron loose and leaving an area of positive charge, a hole, where the electron used to be. The loose electron then moves towards the top and reaches the top N-type layer, which readily accepts electrons. Similarly, the loose hole moves towards the bottom and reaches the bottom P-type layer, which readily accepts holes. This continues as long as sunlight shines on the solar cell. Now that the electrons and the holes have been separated, connecting a wire between the top and the bottom metal electrodes provides a pathway for the electrons to move towards the holes. Flow of electrons is electrical current. One solar cell produces several watts of power. This may be sufficient for running a calculator or a phone charger, but it's not sufficient for running a toaster, for example, which uses 1,000 watts. So, several solar cells, typically 32, are wired together to make a solar panel. Several solar panels are needed to generate enough electricity to power a household. As leaves generate food for plants directly from the sun's rays, solar cells are a viable way to convert the sun's rays directly into electricity that we can use. Future challenges include improving the efficiency by which a solar cell converts sunlight to electricity and making the solar energy cheaper. Of course, solar cells produce electricity only during the day, so storing the electricity efficiently for use during nighttime is another important challenge. Advancements in solar technologies present the potential to power our lives if we just leave it to the sun.
Solar power is responsible for about 1.3% of our electricity, but it's also one that's growing quite a bit. Houses and buildings can also be designed to use solar energy in passive forms for heating water and heating the home itself. But these values of energy are tough to measure, and so they're not really counted in our totals for our energy uses. Costs of solar power are going down greatly. They're getting more and more economical all the time, and the technology is improving all the time. And then there's many areas in the southwestern U.S. that are suitable. Colorado is one that's definitely very useful for solar power. It's renewable. It does not create any air or water pollution. Those are both huge advantages for solar power. Solar cells are not super efficient right now. Only about 18 to 24% of the sunlight is actually generated and transferred and converted into electricity. And you can only generate that electricity when the sun's shining. Again, some of these large solar farms in places like the desert do have some negative effects on the ecosystem as you put some of these very large lots and lots and lots of these solar panels or solar reflectors. They cover very large areas, and those affect things like migration patterns and habitats and can affect the ecosystem as well. Some of the big ideas and important things to remember about all of these different energy sources. We need all of them. We can't do this with just one energy source. They're either renewable or non renewable, and we have to try to find a balance in our use of those non renewable energy sources because we can't just stop using all of them at once. We have to find a balance between all of these things. Some resources can't be used in different locations. For instance, solar power may not be super useful in places like northwestern US that tend to be more cloudy and rainy and dreary weather. You can't use hydroelectric power where there isn't water resources like tides or rivers or lakes. You can't build a hydroelectric power plant in the middle of the desert unless there's a river there. And we really, really have to look at costs and benefits of each one of these, try to increase the ones that are renewable and decrease the uses of our ones that are non renewable, and find a balance between all of these different resources we have to use to meet our energy needs. Thank you very much and have a good day.